Um, I like to thank Griff Smith for reviewing my announcement and my view graphs, and also contributing some things to the talk, because in the process of reviewing things, it triggered things of work that he did, and he sent them to me. And so it turns out that he was involved in a computer graphics sense about the same time I was. Anyway, let me start sharing the screen here. Okay. All right, so we go to slideshow. Okay, I presume everybody can see the view graph. Is that correct?
Yep. Yes.
Okay. So today's talk will be the math behind computer-generated images. You know, the math is really at a high school level. You know, algebra, geometry, trigonometry is really what most of the math people are using. So what I'll be going over is I'll provide an introduction to the basic modeling and manipulation of graphic images as processed via computer. I will describe the world and object coordinate systems used in that framework. I'll describe the mapping of 3D images to a 2D viewport. I'll describe how only the visible surfaces are selected. I'll show how 2D images are enhanced to look 3D with shading. I'll show how to add spectral surface characteristics, image and texture mapping onto the surfaces. I'll show the difference between wireframe models and ray tracing. I'll mention some of the pioneering people in the industry, and I'll be going over the history and progress made over many decades. Okay, just to give you an idea of the wide variety of applications possible with computer image generation. You can have static images, which includes artwork, landscapes, desktop publishing, photorealism. You know, one of the first things that were done really was with fonts, to have scalable fonts, and you know, a line drawing is generated and then it's filled in, you know, within the lines to, you know, paint all the fonts. So this really was the first application. Other applications are engineering applications, electrical, mechanical, computer-aided design, computer-aided manufacturing systems. So people input circuits and mechanical drawings. One of the advantages of that is that, you know, once it's been inputted, besides just printing drawings, wireless can be generated, wire routing, net lists can be generated, and also numerically controlled machines can build things that were in the mechanical system or in the model. Also, it's been used for architectural drawings, 3D rendering of buildings, walkthrough of visualization. I once bought a $50 software architect software package and inputted the dimensions of my newly purchased home. And when I was finished, I was able to do a 3D walkthrough, which was quite impressive, actually. And that was back in the 90s timeframe. Also, anatomical models, you have CT, MRI images, multimodal images. They can build 3D models, prostheses, and crowns from some of this stuff. And, you know, in the late 1980s, I visited a small company in Kiel, Germany, that I found out consisted of 3 people, a doctor, a physicist, and a programmer. And their work was written up in the magazine Electronics. And what they were doing is taking a raw X-ray slice data from computed tomography scans, building a 3D model, selectively removing the tissue, modeling the bones as a solid surface, providing a 3D rotatable view, and sending that to a 3D axis milling machine to recreate selected bones. So this was intended to provide surgeons with an exact replica of the bones involved so they could plan out the surgery. And additionally, custom-made prosthesis could be fashioned ahead of time. So that was pretty innovative, but I've never seen that since. So I don't know what happened with that effort. The other thing is interactive visual simulation and visualization. So that could be used for flight and driving simulators, fluid dynamics, chemical processes, and as far as interactive simulation, usually the requirement is that it's done in real time. So if it's not done in real time, you can go to computer animation. So the full-length movies, short films, commercials. There are other applications like virtual worlds. User interact with avatars and gaming programs. And these are home computers with overclocked CPUs and souped-up graphic boards. And their computations are very similar to interactive simulators. The last is motion capture. This is to capture live human-animal motion points and integrate that with computer models. And this helps understand the physics of biologically motion and also speed up the data points for computer modeling. So it turns out that, back in the 80s, I actually worked for a company. They were building a first-time CGI hardware to do interactive simulation for flight simulator. The project was an FA-18 flight simulator. It was roughly a 5-year effort. I spent the last couple of years on that effort. It had a dome. It was a large 20-foot reflective screen. That was the final installation. It had projectors. They used Schlieren optics. And Schlieren is a case where there's a glass sheet with an oil film on it, and a cathode ray tube writes on this oil film scan at a time, and it bends the oil film so that the intensity changes. And that was really, and then a bright line is shown behind it to project the image on a screen. So this was the only real way to get a image projected that was generated in real time at the time. So I never heard of Schlieren before that, and I haven't heard of it since then. The technology that was used was emitter coupled logic at 25 megahertz. That's 40 nanoseconds. Just to give you an idea of the technology at the time, the Apple II had come out. It had a 1 megahertz clock. The IBM desktop was coming out, a 3 megahertz clock, and 64K memory was about the norm. So this was already, about 20 times faster than commercial hardware. So, the type of hardware it was a parallel pipeline array processor with a CPU controller, and they were all in ECL. And the controller was really an IBM 360 CPU emulator in ECL with some additional instruction to control the array processor. The bus architecture was simple, dedicated buses on all 3 sides between boards. Software was assembly code for the IBM 360 instruction set plus the extended instruction. And the modeling was done separately on a VAX 780 with object modeling, and then had an IBM 360 interface to download it to the array processor. The enclosure was 3 cabinets with about 20 to 25 boards each in pizza box size, roughly. So they were large boards. The cooling was 3 cabinets with large fans behind the graphics processor. The emitter coupled logic, the throughput is about 1 nanosecond but the rise time is 3 to 4 nanoseconds. Wiring delays of 1 nanosecond per foot and had to be added in, as well as some settling time to stay under 40 nanoseconds. And ECL logic is basically an analog operational amplifier that has differential inputs and outputs and continually draws current, unlike TTL, which only draws current when switching. So the power supply for this was tens and hundreds of amperes of current, and it was quite a noisy environment. Now, anybody working in this field will quickly learn who some of the pioneering people in the AGI industry are. There's Evans and Sutherland, who founded the company Evans and Sutherland. Ivan Sutherland was really the key person. He had a degree from MIT, and I think he came out to the University of Utah. And just about all these other people, even if they got degrees somewhere else, they came to the University of Utah and got their PhD in either EE or CS or physics or whatever, and made significant contributions to computer graphics. So that was like the place to be. So you had Edwin Catmull, who also turned out to be co-founder of Pixar. Most of his work was done in the 70s and 80s, maybe 90s, and he only got the Turing Award in 2019 for CGI contributions. You had John Warnock. He was the person behind Adobe PostScript, and he's also known for the hidden surface Warnock algorithm. You had Scott Hunter, who got involved with Oracle. You had Jim Clark, who founded Netscape, left and founded Silicon Graphics, which produced the high-end graphics terminals that cost like $100,000 to $200,000, and also known for his fast 3D rendering. You had Henri Guerard, who developed the Guerard shading algorithms. You had Bui Tuing Fong, who developed the Fong shading algorithm. You had Jim Blind. He was a JPL computer graphics expert and known for the Blind-Fong shading algorithm. You had John Turner Whitted, who did the first ray tracing algorithm at Bell Labs in the 70s. And you had Foley and Van Dam, who co-authored a graphics book, which superseded another graphics book that was used, but their book became the Bible for the CGI world. Okay. Let me just mention about Jim Blinn. When our Jim Blinn joined the old guard, I was curious whether he was the Jim Blinn, and he assured me he was not. So anyway, so, let me just mention two technology laws. One is Moore's law, which I'm sure you've heard of. So it's named after Gordon Moore, co-founder of Fairchild Semiconductor and later Intel. So his observation was that the number of transistors on integrated circuits doubles every 2 years. Processing performance doubles every 2 years. Other people have scaled that back to 18 months. One thing that's interesting about the array processor I worked on in the 1980s is that 10 years later, you could get that on a graphics card on a CPU with a faster clock speed, and it could do pretty nearly everything that huge machine could do. Then there's the other one called Blinn's Law. It's named after Jim Blinn, who did the JPL Voyager animations, Sagan's Cosmos animations, and the Blind-Fong shading. And so his observation was, if you know anything about people that spend time putting together animation sequences, they usually have as many computers as they can get, and they usually spend months putting together the animation. So you would think that with faster computers, they would be doing it in less time. However, his observation is that rendering time tends to remain constant even as computers get faster. Animators prefer to improve quality, so they will render more complex scenes with more sophisticated algorithms, which naturally require more computing power. So generally, the time they spent generating one of these animations doesn't decrease. Some of the films done by the CGI industry, Future World was a very early one, had an animated face and hand. Tron was the movie that came out at the time I was working on this array processor, so I had to go out and see it. It was the first CGI movie with a mix of actors and graphics. It was like 80, 90 minutes long, so that was a first. It was still very simple. About a decade later, Toy Story came out, so this was the first entirely computer animated film, and this, with a much more palatable scenario storyline. Now, I won't go into the others which I listed here, but Finding Nemo, Ratatouille, Wall-E, and Zootopia are worth seeing. And as processors get faster, the graphics improve, notably with human faces, hair, water, and windblown hair. It's very difficult to get all these things right. Okay, so let's go on. So the overview of computer image graphics image generation is, people work with a coordinate system. I guess there's many possibilities, but most people stick with rectangular. And it's easily allowed for mapping to a 2D viewport. For modeling, object modeling, there's really two ways to do it. One is with polygon objects, and the other one is with mathematical objects. So polygon objects are piecewise approximation. One way is to have a unit cube defined by 4 points in 2D or 8 points in 3D with the corners at 0, 0, 0 or 1, 1, 1. And the little diagram at the top is just a 2D unit cube. So it's got 4 points, 4 edges, and 1 surface. And of course, larger objects can be made with multiple cubes pieced together with just a larger multi-point surface. And the operations done on these are resize, move, and rotate using scaling, translation, and rotation operations on these points. Now, the other way of doing it is to use a mathematical object and have an exact representation. And these are generally used for ray tracing. Now, once these things have been modeled, to make things look realistic, it requires light sources and shading. So one or more light sources and modeling methods are used for spectral and shading algorithms. And once all that's done, then there's a complex scene, and only put the processing power where you need it. So there's algorithms to do hidden line and surface removal. So show only what is visible to the observer. And once that's done, a 3D model needs to be projected to a viewport, which is a 2D surface. So it means to clip and map and rasterize the 3D object models for the final display. Okay, so I'll cover translations, and that's to move an object. If you look up here, there's a XYZ representing a point, and if one adds a translation factor, that point can be moved to a new XYZ location. So the translation factor can be the same or it can be different for each axis. And this is, the first set of equations is spelling it out, but this can be put into vector form, or into matrix form, which are really 3-row vectors. And a more concise representation is just to use the single letters to represent the vectors. So here's a diagram of how translation works. Here's a house. It's got a point at 4, 5, and 7, 5. By adding minus plus 3 and minus 4 to X and Y, it moves, and applying it to all the points, it moves the house over. And so that's a simple example of translation. Now, the other thing is to resize an object by scaling. So if here again are the equations for scaling. So you have X, Y, Z is the original point, and adding a scaling factor to these points, multiplying by a scaling factor to these points. So if they're all the same scaling factor, the object will retain its shape. If they're otherwise, it's differential scaling. And putting this into matrix form, it's a row vector for the original and the scaled point, but the matrix is all zeros except for the diagonal, which has the scaling factors for each axis. And the compact notation is just to use the letters for the matrices. So here's this example of the same house. And so in the X direction, it's divided by 2. And in the Y direction, it's divided by 4. And it's applied to all the points. Then you can see how it scaled. Now notice also applying scaling meant that it moved the house to a different central spot. So something I'll talk about later is to avoid that, they would translate the centroid of a house to 0, 0, do the scaling, and then move it back to where they want it to be. All right, so the third thing is rotation of an object. And here's the rotation about the z-axis. So the point representing the object can be rotated to reposition an object to its location. Positive angles are measured counterclockwise from the x-axis toward the y-axis. The object's centroid must be translated to the origin before rotation and then translated back if you wanted to rotate it about the centroid of the object. So here's a point P. It's actually being rotated about the point 0, 0. And here's P prime where it's going to wind up. Its original angle is angle phi. It's going to move an additional angle theta over. So just taking the adjacent, distance here will give you r cosine theta, and the opposite will give you r sine, r cosine phi and r sine phi, and these are these equations that you start out with. So this is a representation of X and Y. So we take these equations and we add that additional rotation of theta. And if we multiply that out using the sum of angles formula, we get this equation. And if you look at, so this equation actually contains the original r cosine phi and r sine phi, and replacing those with X and Y gives the final equation, which in terms of the original point and the angle being moved. So that's how the rotation is done. Now this, physicists and mathematicians usually use a right-handed coordinate system. In computer graphics, they use a left-handed coordinate system. And the reason for that is they want the z-axis to go away from the viewer into the page. So X goes to the right, Y goes up, and Z goes into the page. So it winds up to be a left-handed coordinate system. So this first equation here, is basically the matrix form of what I just showed you before, except now it includes the z-axis, and there's a 1 here to keep the z-axis happy. So this is the matrix form, and the first equation is rotating the XY plane about the Z axis. But the same thing can be done, rotating about the YZ axis, YZ plane with respect to the X axis, and that's this version. And then the last one is to rotate about the ZX axis in the Y of ZX plane in the Y axis, and that's this version. Now, as you can see, the sine cosine terms move around, but there's in the diagonal, there'll never be a 0, there'll always be a 1 somewhere. And what's interesting now is you can actually concatenate all these into one matrix. And however, they have to be done in a specific order. So doing the rotation about the y-axis first, and then the x-axis, and then the z-axis is the order needed. Otherwise, strange results are gotten. But these three matrices can be multiplied together and then have just one resultant matrix to multiply the points and get the proper rotation. Okay, so here's a rotational example in 2D. So that the steps are translate the centroid to the origin of the coordinate system, scale the object if needed, rotate about the appropriate axis or axes, translate the centroid back to the intended position. So here's the original house. Here it is, whoops, here it is. The centroid is moved to the origin of the coordinate system. Optionally, it can be scaled, the rotation can be applied, and then it's translated back to the final position or the intended position. Now, if that's not done, like here's this upper diagram of rotation of a square shows that if it's not done, then it'll rotate about, this one rotates about x equals 0, y equals 2, because this line here intersects the axis here, wherever that line intersects. So you have a rotation, but it's not about the centroid of the object. Okay, now what happens when you want to try to consolidate all these operations? Well, there's a little bit of a problem because some of them are multiplication, some of them are addition. One of them is addition. And how do you reconcile that? Well, they reconcile it by using an augmented matrix. So what they do is they take the row vector, which has x, y, z, and they extend it by 1 and put a 1 there. So all points will have this form. They'll take the matrix and make it instead of a 3 by 3, they make it a 4 by 4. And there'll always be a row of 1s here in the diagonal. So for translation, on the left, I have what the matrix looks like not being augmented. So the top one on the left is translation, the middle one is scaling, the bottom one is the concatenation of all the rotations. And changing it to the augmented matrix on the right, the top one is for translation. So TX, TY, TZ are at the bottom row here. And with ones on the diagonal for scaling, the scaling factors are on the diagonal, but since it was extended, they have to put the 1 here to keep the extra 1 in the point vectors. And for the translation, rotation rather, you have the 9 rotation values and then the 1 in the diagonal. And if you multiply everything together, the bottom one is what that would look like. There's some values in the 3 by 3, the translations are at the bottom, and the 1 is sitting on the diagonal here. So that simplifies the hardware because otherwise, and the programming, because otherwise for each operation you have to check, well, what am I dealing with? Okay, send it to this routine or that routine. And this is especially useful for array processors where now you can just send all the points to one translation, one matrix to do the translation, scaling, and mapping, and not worry about and have it come out correctly. Anyway, when modeling this, people generally use various coordinate systems. So the first one is the world coordinate system. So all objects are referenced to this. And here is an example, is a stylized tricycle with 3 coordinate systems. Okay, so one is the world coordinate system, then there's coordinate system just for the tricycle, so the body of the tricycle can move in some direction, but then the tricycle itself has other moving parts, and one is the handlebars can rotate, another one are the wheels can rotate. So in this case, they have another coordinate system for the wheel. Okay, so so what this allows is easy computation. Somebody can be working with the tricycle all by itself or the wheel all by itself and work out a bunch of sequences. And then once that's worked out, they can map them all back to the tricycle, and then the whole tricycle can be mapped back to the world coordinate system. Okay, so moving on from there. So this is a conceptual model of the 3D viewing process. So once we have the 3D world, we want to be able to project it onto a screen. So the first thing to do is clip the scene against the view volume. So this eliminates non-visible parts of the scene. The second is to project the 3D scene onto a 2D plane. And then the next is to transform it to normalized device coordinate. And so these normalized device coordinates will generally be from 0 to 1. But in the last step is there's so many pixels in a, so many pixels in a line and so many scan lines. So that's finally translated to physical device coordinate. So this is just showing, each of the steps that need to be done to get the final image. So, the world coordinate system is in floating point and covers the entire scene. The viewport is a normal device coordinate system, arbitrarily from 0, 0 to 1, 1. So here's a mapping from a window in the world coordinate system. It's mapped to a viewport, 0 to 1. Okay, one of the other things that needs to be done is to do some kind of projection, geometric projection. And there's 2 basic types. One is perspective, the other one is parallel. Perspective, the center of projection is at the vanishing point for shortening. This is how most artists do artwork. And, it's a visual effect that's similar to photographic and human visual systems. The other way of doing it is parallel, where the center of projection is at infinity. It's usually used for engineering drawings because all measurements are now to scale. And within the parallel, there's 2 ways of doing it. One is orthographic, which means the projection is normal to the projection plane, and the other one's oblique. And within oblique, there's 2 styles, cavalier and cabinet. So to do these projections, it generally means that the scene is multiplied by another matrix to do the projection. And here, the first one is the matrix for perspective projection. So there's 1 along the diagonals, and this term has a 1 over d, where the d is the distance from the 0 point to where the projection plane is. For orthonormal projection, there's 1s on the diagonal except for this one. And for oblique, there's 1s on the diagonal except for that one, plus some L cosine terms and sine terms of angle alpha, which is the oblique angle, represents the oblique angle. Okay, so after that, I'm going to talk about some of the hidden I'm going to talk about, hidden line and hidden surface removals. There's quite a number of ways which that this will be done, can be done. One is called the, and this is just for removing hidden lines. And this is called the floating horizon algorithm. So this removes hidden lines from a 3D representation of surface functions. So f of x, y, z equals 0. And it's generally used by graphic display routines and applications like S and S plus and so on. I remember when I first came across S, I put in the function for a Mexican hat, and there's a way to plot it. And when you get a plot, you get something similar to what you see on the bottom, except I think it also plots equally spaced lines in the other direction rather than just the, this is just in the Y direction. It'll also do equally spaced lines in the X direction. So this is similar to the Mexican hat, except it's upside down and it's on a Ripley surface. So it's sort of similar, but a little bit different. Now, I'm not actually going to go through the algorithm. This is a very terse description of the algorithm. The actual algorithm in pseudocode is in one of the reference books, and it's like 2 pages long, so it's a little bit involved. So another thing about hidden edges and surfaces, there's 2 approaches. One is image space, the other is object space. So image space are what surfaces are seen on the viewport scan line, and object space is what objects are seen in the scene. So one way to do this is, let's say perspective transform was done, you would get maybe a trapezoidal volume, which represents what's in the scene, okay? But the fact that these lines are at an angle makes it hard to clip, makes the clipping problem harder. So what they'll do is they'll change this trapezoidal object into a rectangular box, and that way it's much easier to clip the scene, because you can arbitrarily set these things to 1s and 0s, boundaries, and just clip against that. And there's actually a little bit more work involved, but I'll leave that to the reader, Anyway, another way is for removing hidden edges and surfaces is to use screen extents and minimax tests. So, the upper left here is 2 triangles overlapping. If you have 3 points, you can put a square around it, and that's like the maximum extent of the triangle. If the extents overlap, then you say, well, maybe the triangle is overlapping. The drawing to the right of that is the extents are overlapping, but the triangles are not. So how do you decide whether it is overlapping or not? Well, what they do is, if you move all the way to the right here, they'll take one of the edges, put an extent box around that, take the other edge, put an extent box around that. The extent boxes are not overlapping, so therefore the triangles are not overlapping. And there's other methods to resolve using a depth sort algorithm. And these are sort polygons by the largest z coordinate and resolve the ambiguities and scan convert each polygon in descending z order. The other way I want to mention is it's possible to do surface normal checks. So if you have 3 points that has 2 lines, and if a cross product is done, that will yield a surface normal. If the surface normal is pointing away from the viewer and it's on the backside of an object that's completely enclosed, obviously that surface is not going to be seen, so that surface can be discarded. And that also helps simplify the computation. Another way to remove hidden surface is a Z buffer or depth buffer algorithm. So this is actually, I think, the way that this array processor used to remove hidden surfaces. And so the way this is done is the Z-axis is 0 at the viewpoint. The depth value of Z is stored in the buffer and compared to each new object. And then interactive use of for real-time applications, interactive use of 2 display buffers are used, one for active and one being worked on. So the one being worked on is done during one frame interval, and then it's swapped out. Then that one becomes active and the other one is worked on. So it continually toggles back and forth between 2 buffers. So what they do is they calculate a polygon depth Z at XY, at pixel XY. If Z of XY is less than the Z buffer value at pixel XY, then it places the value of Z into the Z buffer. And they're, and this is to be able to check it against the Z value of another polygon at a later time, and then place the value of the polygon into the Z buffer at pixel XY. And, basically they're using the equation of a plane and they're solving for Z to do the Z depth. And however, since they're moving across by 1 pixel at a time, delta X is really only 1, so it simplifies to the equation that's shown at the bottom. Now, there's another way of doing this, and this is probably more suitable if somebody's using a general purpose processor and can create linked lists of a sort, and they would create an edge table and a polygon table, and they would sort the coordinates within this, the polygons within this, and they would process it that way. So I'm not going to actually go into that. Since I mentioned the Warnock algorithm in the beginning, this is another way of doing it. Basically, it's easy to decide if a polygon is visible or not, because if it is visible, just display the polygon. If it's not able to decide it, just subdivide the area into smaller and smaller areas and reevaluate. So there's 4 possible relationships that do not need divide and conquer. So the left is a surrounding one. So it's completely shaded, just just fill in the polygon color. The next one is an intersecting polygon. It intersects the area. So you first fill in the background color, and then you scan convert the piece of polygon that's sticking into that area. The third is a completely contained polygon, and you can just scan convert this. And the third one is a disjoint fourth one is a disjoint polygon, which is completely outside the area. So it doesn't even show up, and just use a background value. Now, if there are multiple polygons, just keep subdividing and subdividing until the problem gets simpler. It gets down to these 4 cases. Okay, so once hidden surfaces have been removed, the other thing is to do some kind of shading. If there's no shading at all, everything looks like a blob, and there's no 3D, possible. Let me first start pointing out, talking about this VW model. At the top right, there's a wireframe model for the whole VW bug. This turned out to be a popular image to work with. And below that, on the left, is the polygons are shaded with a flat shading. And of course, it's a little bit hard to see, and it's also hard to see in the book, but each one has a specific density according to the angle of reflection here. But if a certain kind of shading is applied, then everything looks nice and smooth. Okay, so let me point out, this black and white, the grayscale cup here, what looks like a grayscale cup. On the left is flat shading, so you can see the large sizes of each polygon, and it's shaded according to its angle toward the observer. And of course, one possibility is just to make the rectangles, polygons smaller and smaller until they occupy a pixel. But the problem with that is, if the object moves away, then there's too much computation. And if it moves too close, then you're back to this scenario. So the easier way to do it is just to apply a shading algorithm. And in this case, on the right is an example of garage shading. And you get a nice smooth surface, and there's no visible edges anymore. This sphere here, it's an example of two type, flat shading and garage shading and Phong shading. So a relatively coarse sphere can appear quite smooth with garage shading. However, an improvement on the specular reflection has been done with Phong shading to make it a little bit more realistic. So, without shading, things would look awfully cartoonish if it wasn't to try to put in shading for 3D effect. Now, for shading models, there's two ways it can be done. One is a diffuse reflection, and this is for dull matte surfaces, light scattered in all directions. It basically reflects back the color of the surface. The other one is a specular reflection. This is for shiny surfaces. At the highlight, you don't see the color of the surface, but you actually see the color of the incident light. And so this follows Lambert's cosine law, which relates to the reflected light of the angle between the light direction and the surface normal. Here's a diagram of the specular reflection case, although it covers the diffuse one as well. This line, horizontal line, is the surface. Perpendicular to it is the surface normal. The vector L points to the light source. It's off at an angle by theta. If a light bounces in, it'll reflect off at a complementary angle, angle theta from the normal in the other direction. So that's the direction of reflection. And if there's a viewer at vector V, there's some angle alpha between the viewer and the direction of reflection. So the diffuse case, the illumination of diffuse is the ambient illumination times the K factor for ambient plus the illumination for the light times the diffusion factor times cosine theta. So this is dependent on how the light source is relative to the normal. And of course, cosine theta can be rewritten as a dot product between the vector L and the surface normal. And what they also add, because light falls off as 1 over r squared, or really 1 over the distance, they use r distance to simulate that, but it doesn't quite work as well, and they add a constant of some value to get the effect that they want. Now for the specular reflection, they have to add where the viewpoint is relative to the angle of reflection, direction of reflection. So they add another term here, W of theta cosine to the n of angle alpha. So cosine alpha is really arc dotted with V, and that will be to the nth power. And this W of theta will be converted to a constant related to theta of the angle. And the theta of that angle is shown down here. So at the graph shows 0 through 90 angle of incidence, and then what that W of I would be. And it shows it for different materials. Here's one for glass, here's a curve for gold, and here's one for silver. So depending what type of surface you want to simulate, they would use one of these curves anyway. And here's just a picture of comparing Phong with Torrance spiral models for a metallic sphere. And the top left is for a 30-degree angle. The top right is for a 70-degree angle. And here at the bottom are examples going from almost front illumination to rim backlight cases. And so again, it depends on what you're trying to, how you want things to look as far as deciding what shading model to use. So the Torrance spiral model is a little bit harsher, but maybe that's desired in some cases. So one thing about these shading models is, for every surface, surface normal can be computed. You need 2 lines, 3 points and 2 lines. So here's 4 surfaces with each of their normals. The vertex normals are calculated from the adjacent surface normals, and they're used for shading in the Gerard case. And so at this vertex, there's a vertex normal calculated, and it's really just the arithmetic sum average of the surrounding surface normals. For the normal vector interpolation for shading using Phong, basically he's using the Gerard shading, but then if here's a triangle that needs to be interpolated, you have intensity I1, I2, I3. They can be interpolated, so you have IA and IB at the scan line, and then from IA to IB, it can be further interpolated. And this is what Phong shading is doing. So here's an example, of another shading model. On the left, it's flat shading. On the right, it's Gerard shading. And it's much easier to see the flat shading panels. And this is done for face, and all these sharp edges can be smoothed out with Gerard shading. And the way this person actually used his wife as a model, and he inputted that into the computer, and then he applied a shading algorithm to get that. Now, the thing about using polygons is sometimes you want to do very elaborate surfaces. So there's something called Bezier curves and surfaces. It's an alternative just to creating arbitrary polygon with points. It was developed by the French engineer Pierre Bezier for CAD/CAM applications, and it was based on a 1959 algorithm by French physicist Paul de Castelnau. And anyway, so what you see here is you see straight lines with points at the end, and these points serve as control points, and by adjusting the control points, then a curve can be mapped out. And on the top left is 3 cases where there's a gradual curve. Whoops. And by adding control points, you can make it bend more at the bottom, and finally it bends completely and follows this triangle. So the way it's not terribly complicated, but let me work from the inside out. The C of Ni is just the binomial coefficient, which is expressed in terms of factorial. This is used as an argument to the blending function, which is B of I and N. And so that's times U to the I times 1 minus U to the N minus I. And this is your blending function. And this blending function is used in the summation over the number of control points. So pi is a control point, and blending function is the b of n and I is a control point, the ith control point, a blending function for the ith control point, which will end up in a nice curve. Now this can be extended in 2 dimensions to get surfaces. It's very similar, except there are 2 summations and 2 blending functions. Now, one problem with Bezier surfaces, for instance, if you have 2 and you want them to match up at the boundaries, it may be a little bit difficult. So they came up with something called B-spline curves and surfaces. And so what this does is, so complex geometric constructions are required to get continuity when piecing curves and surfaces together, and they can be avoided by using mathematical constraints, and it uses a set of blending functions that have local support only. So the basic equation looks very similar, except for B, they call it n, and n is this spline function. It's either 1 or 0, depending where its extent is. And this is the description for n. And in 2 dimensions, it's 2 summations and 2 spline blending functions, n. So here's a case where this was a jet intake engine modeled for a CAD system. I imagine there are at least 2 Bezier curves. One is out here and one is on the inside, and they're probably matched here. But again, there could also be some matching here, and the matching would be done with these spline curves. Okay, one of the most popular objects modeled is the Melita brand teapot, aka the Utah teapot. And this was first modeled with Bezier curves using control points by Martin Newell. So he was sitting one morning opposite his wife. She was making tea in this pot. He looked at it, he says, this would be a really nice test model for doing shading algorithms and testing for all kinds of things. And so he quickly drew that up on a sheet of paper. When he got to work, he input it into a Tektronix interactive terminal where he could input it as Bezier curves, and then he generated the teapot. So the picture on the left is the actual teapot. That's what it looks like. The 2 pictures on the right, the upper one is flat shading of a white one, and the bottom one is smooth shading for like a metallic one. And if you look at it, if you look at the metallic one, I mean, the handle creates a shadow. So light from the top creates a penumbra shadow down here. And also light hitting the bottom surface creates a bright spot at the bottom of the teapot. So this winds up to be a very useful object to test all kinds of, to make sure all the graphics algorithms are working correctly. And it gets used over and over again. Now, all this stuff is all smooth shaded, but there's detail left out, and the way they put in some detail, one way is to do texture mapping from a digitized photograph or some texture detail, and they basically map it. If this part is the pattern array, it gets mapped onto the surface, and then it gets mapped onto the observable screen. So down here is an example of a photograph mapped onto a bicubic surface that's a cylinder. And this is courtesy of one of the pioneers, Edwin Catmull. Now, he developed also another way of doing surfaces, and that is by perturbing surface normals before using the shading algorithms. And this is used for getting, like, let's say, an orange peel effect on a surface. Now, another way a surface can be, detail can be added is using fractals. So they start out with a mesh of quadrilaterals. They subdivide the surface a number of times to create a rough, jagged terrain using fractal algorithm. And the final step is to do hidden surface removal, followed by an appropriate shading model. Now, the shading model has to be carefully selected, because if it's too smooth, then it kind of lost the effect of the jagginess of this mountain range here. So this mountain scene was done by Laurel Carpenter, Boeing Computer Services. And you can imagine this was probably used for doing, doing a scenario for flight simulators to give a realistic effect of mountain ranges. Now, to jump to something completely different, if one is not using polygon models, one is doing ray tracing. Now, ray tracing is photographically very accurate, but it's computational very expensive. So basically, a ray is traced from the eye of the observer through each pixel in the viewport to the surface in the scene. But once it hits the surface of the scene and it's reflected to some other object in the scene, it has to compute all those sub-reflections, because it alters the light actually seen from at that pixel. So the light ray is broken into three parts. One is diffusely reflected light, spectrally reflected light, and refracted light, as in glass. And all three examples are here. The checkerboard here is the matte surface, so it's diffusely lit. This sphere is silvered or mirrored, so this has specular reflections, and this is a glass sphere, so it has refracted light. So this was this is an example by Turner Whitted from Bell Labs, done in the 70s, and it's found in almost every textbook. So this is just an image of, what's really happening with ray trace. The observers where the camera is, there's one, it's going through 3 pixels here. One is hitting the matte surface and just taking that color on. The other one is hitting close to where it's getting some reflection from the light source, so it has to cast another ray to the light source and figure out what's happening there. The other one is hitting the shadow point, so it has to cast the ray to the light source and figure out the degree of the shadow. And these are another view of it, talking about the math model behind it. In step 1, there's an equation of the sphere, there's an equation for the ray, and there's an equation for the intersection with the sphere. And there's 3 cases: either it's blocked by the sphere, it's tangential to the sphere, or it passes by the sphere. And then they need to use some kind of illumination model, so they use the Blin-Fong illumination. And this equation here is exactly what I showed before. And with refraction, they need to use Snell's law. And so Snell's air has a value of 1, for glass is 1.5, and you plug it into that equation to get what's happening there. And then finally, you have to do some kind of shadow modeling, and that's the 4th step here. And it's just the ratio of all the rays to figure, the visible rays to the shadow rays to figure out how much light hits the area. Now here's a more elaborate ray tracing model. I really like this one. It's as if it were taken by a camera. There's some kind of light source in the upper right-hand corner, which is off screen. It comes down at a diagonal. You see like window light over here. It's hitting each one of the glasses. There's actually a plane of focus which goes right along the bottom here. The dice are in perfect focus. This glass is in perfect focus. This one is in perfect focus. The bottom of this glass is slightly out of focus, as is anything behind it. You also have a glazed picture here which has a really nice out of focus effect, but it also gives the appearance that it's really a glazed picture. Also, there's an ice cube in this glass, and you have all the reflections and refractions that go, through the glass and through the ice cube and into the objects behind it. So this is a really detailed scene of what can be done. Okay, the next one may look simpler, but it's actually more complicated to compute because a light ray hitting any one of these glass spheres will just bounce around, maybe 100 more times, and each one of those rays have to be computed just to figure out what the light intensity is at the point of interest, at the pixel of interest. And, and this is really at the back end, when stuff is displayed, it's usually just, back in the old days, it was displayed on a CRT, and that was for a very long time until LCD displays came along. There's basically a frame buffer for red, for the three colors RGB, and they're fed to, it's usually 8-bit per color, and they're fed to 8-bit D to A converters, and they each drive one of the three color guns on the CRT. However, there's something called, since the CRT is nonlinear, there's something called like a lookup table, a gamma correction, and this is done through a lookup table. So in this case, they take 8 bits and feed it into lookup tables, which output 10 bits. So now these things go to 10-bit D to A's before they go to the color gun. And so on the right here is what the monitor response looks like and what the gamma response looks like, and they'll cancel each other out and get a linear system response. Now, from the viewpoint of a monitor, the color, here's an RGB color cube. 000 is black, white 111 is white. The corners are either the primary or secondary colors. So this is a simplistic view of what the color map looks like from a monitor's point of view. Back in 1968, there's a physicist, Victor Weisskopf, who wrote an article, How Light Interacts with Matter, and he came up with this diagram. And if you notice that, this is something that Griff Smith covered in his color spaces talk, in terms, this is the CIE chromaticity diagram. The white edge here is what the human eye sees. This black triangle here is the RGB color space. And when he wrote this article, he determined that, what's really important is this area here, and it's within the RGB color space. And that's all that's needed. Of course, later on, digital photography comes along and people are not happy with the limited color range. And then they added Adobe color spaces and other color spaces. But you'll have to watch Griff's talk to see the rest of that. Now, Alvy Ray Smith is another key person. He developed the super paint program, and he needed a color model for it. And he developed this double hex cone system, hue, luminosity, and saturation. So here's black, here's white, here's the halfway point, and around this hexagon are the primary and secondary colors. Anyway, animators have quite a bit of imagination. Here's something done about the same time Tron was done. It was called The Works, done in 1980. People in New York Institute of Technology worked on it from 1979 to 1968. There was a team of 60 people. They had this very ambitious goal. The graphics are way better than Tron. However, given the technology they had at the time, they could only produce 10 minutes out of the 90 minutes of animation. And they finally figured out it would take about another 7 years to finish it, and so they left it as unfinished work. But this is a giant ant that's being used as a sort of like a construction vehicle. The dome lids pop out, and a little robot can sit in the seat and control it like it was a construction vehicle. Anyway, here are some of the pioneers in computer-generated images. Here's Evans and Sutherland. You know, Evans got his PhD at MIT and EE in computer science. And then he came to Utah. And he's like the father of CGI. He got the 1998 Turing Award. And just about all the other people, no matter where they got their degrees, they wound up coming to Utah and getting degrees there. So Evans got his physics degree and PhD at Utah. Edwin Catmull, he got his BS physics and computer science at Utah. And John Warnock, he got his PhD in EE at Utah, and he did the hidden surface algorithm, which I talked about. And he says this was the shortest doctoral thesis ever made. You have James Clark. He also got his PhD at Utah. And this is Turner Witt is probably the only exception to that. Henri Girard, he studied in France, but he came to Utah and got his PhD there, and he did human face modeling and garage shading. Fong, he's Vietnamese, but he came to France and got his engineering degree there, came to Utah, got his PhD there, developed the Fong shading model. And unfortunately, he died of end-stage leukemia at age of 32. James Blinn, he also came to Utah, got his PhD there, and did a bunch of nice work after that. These are the two people from France. They're behind Bezier curves and the Castello's algorithm, but they stayed in France. But there was quite a bit of work done over there to start with. Okay, so anyway, in summary, we had an introduction to the basic modeling and manipulation of graphic images as viewed via computer, processed via computer, described the world and object coordinate systems, described the mapping of 3D images to a 2D viewport, described how only visible surfaces are selected, showed how 2D images can be enhanced with 3D modeling, shading, and how to add spectral surface characteristic and image texture mapping onto surfaces, show the difference between wireframe models and ray tracing, mention the pioneering industry and people in industry, describe the history and progress made over many decades. So here's some books. Here are the 5 books that I own, that I've accumulated. ACM had transactions on graphics. IEEE had transactions on visualization and computer graphics. I have like 20 years of issues of that, but unless somebody's actually involved in work and has time to read that, I really couldn't do much with it. I did attend one SIGGRAPH meeting in Boston, which, is sponsored by ACM, and that was quite interesting. Here are some of the references for CGI. And here's some links to the pioneers, some of the feature films, and some of the video clips we'll be showing shortly. So at this point, I'm going to stop sharing. And
You guys, if you have a question, you know what to do. Raise your hands. And we'll, okay, Mark, go ahead.
Yeah, to start off, thank you. This is not an area that I knew anything about, and now I feel like I know something. And I understood the concepts of the math. So a lot of this work was done from the 1970s up to 2000, according to your sources. Can you tell us anything about what's on the frontiers right now? Like what related issues are being developed or researched at this time?
Well, I mean, I kind of left the field back in the 80s, and all I can say is, because I still look at some of the feature films and I can see that the techniques have greatly improved. And I'm going to show that in some of the video clips, going through time up to 2020, and you can see the difference. And the other difference I see is some people will actually start using ray tracing, which is very computationally intensive, but you get excellent results with it. And you'll see that in some of the clips I'll be showing afterwards. So, but the algorithms get more and more complex. Obviously, if you have more computing power to throw at it, you can easily do increasingly complex algorithms. And like one of the things that they do later is, in the beginning, they can't really model difficult things like hair and texture and water and stuff like that. And they've gotten really fairly good at that using the polygon methods. So I find that, but I'll show you in some of the clips later.
Just one follow-up. In your readings, what kind of participation do you see for artificial intelligence in this area of rendering? Do you see any scope for it?
Well, yeah, I actually do. I mean, one thing I didn't mention is, I was taking a course on DNA, and there was actually a video clip that showed the animation of how this one molecule, as a cell divides, it has to split the DNA and recreate it, recreate a copy of it, and it did this as an animation, and you could never see this in actual life. All they can do is model it chemically in the way it's supposed to work, and then make a graphic film out of it. And it's really just amazing that they can do that. And as far as AI, I mean, I've seen the one talk about convolutional AI, and that's very difficult to understand what's happening at the hidden layers, but they're using graphics to give a window into what the algorithm is really doing. So there's many places that graphics can help, visualize things that normally that are hard to visualize, can't be visualized, or difficult to understand. So that's where it's being used. Okay, next.
Well,
Well, Walt, congratulations on giving us 9 courses in an hour and a half.
Yeah, that's your typical comment. I always cover everything.
But I found it fascinating. My question is, how are computer games produced these days?
You're talking about
The software platforms that are used to create computer games.
on the internet or on the desktop, or?
Let's say I want to create a computer game to put on the internet.
Oh,
What software platform should or is being used? Because I understand that's a booming business these days.
yeah, I mean, it is a booming business. Unfortunately, I really don't keep track of any of that stuff. So,
So an opportunity for a follow-on talk.
Yes, an opportunity.
Okay, thank you.
If somebody wants to step up to it. Okay, George.
Great talk, Walt.
Okay.
Really enjoyed it. My question actually answers or adds on to Mark's question about AI. If you probably have been reading about deep fakes, and that's where they can take an image and replace the image with another person's face or a whole body. And actually, the latest NVIDIA talk by the CEO actually had a minute clip in there, which was totally animated, deep faked, and people couldn't tell the difference. One of the things that's making this possible is, again, with NVIDIA. Their graphics cards have built into it AI capabilities. And that's what's allowing a lot of it. Some of the programs that are out there will actually repair. If you have a torn document which has sections missing, it'll actually repair those sections. Again, it's taking what it sees or what it perceives in the background and tries to fill it in the best it can. Again, it's two things are happening. One, it's becoming extremely fast and easy. These boards are typically under $1,000 now. And the only problem is you can't get them because the Bitcoin miners and everybody else is looking for them. And it's something that's still progressing, and you're seeing it being rolled out, for example, in Adobe Photo. It actually has an AI application or an add-on that can enhance your photos. So you can take a low-res photo and enhance it such that it becomes equivalent to a high-res photo.
Yeah, I mean, since I'm a photographer and I use desktop post-processing, I mean, there's some amazing software out there right now that, but that could be another talk.
Yeah. Okay.
Okay.
Paul?
Yeah, well, I was going to ask about deep fakes too, so thank you. But couple other things. Well, is there a role for quantum computing here? We read about a big breakthrough yesterday.
What was a breakthrough?
Well, I forget where it was, but somebody's discovered how to use some sort of a crystal and a sort of a whole magnetic plane in order to control millions of qubits instead of half a dozen. Control them all at once.
So the question is, how can graphics be used?
Well, just in general, does a computing model of quantum computing seem to be a good match for the computing demands of generating images of these kinds? I mean, for instance, ray tracing. We sort of have the notion of what ray tracing is all about. Each ray, you have to sort of trace it around. You've got a scene that's defined in terms of a bunch of objects, and each object is itself modeled as maybe either a geometric object like a sphere that has an equation, or a wireframe object that's got a lot of complication. And there might be hundreds of these objects. Each one has its own sort of subroutine that defines the model itself. And then you add these all together and combine them, using translation, rotations, and these various things to create a scene. And now you've got to fire individual photons through the scene and see which of those objects they hit and where they bounce and where they split and da 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 da. So that's the computational demand. Now, is quantum, maybe this is a question for Al, because he gave the talk on quantum computing. Is that the kind of computation that ultimately quantum computing will be good at?
Paul, if you can do those computations with unitary transforms, then quantum is just right. But on the other hand, remember that unitary transforms are reversible. So for example, you can't do floating point in quantum. So, and the other issue is if you have lots of qubits, you'd like to be able to control them independently. And this is what's limiting the number of qubits that can be constructed by companies like IBM or Google in their NISC, noisy intermediate scale quantum computers. The physicists seem to be able to create physical apparatus that can control larger numbers of qubits at the same time, but programming them is difficult.
Now, the only thing I have to add is, when it comes to ray tracing, it's actually best matched to, a bunch of concurrent processors where each processor does, let's say, 1 pixel, and that's all it works with. So if you have 1 million pixels, then you have 1 million processors to compute that, and it would speed up ray tracing. So it lends itself very nicely to parallelization, whereas the other, the polygon model, not as much, Anyway, so Papi, you have a question?
Yeah. How much is the artist play a role in this computer graphics? I have a not young, my daughter's friend who does a lot of animation for Sesame Street and things like that. I wonder how would the artist play a role in creating this animation?
The artists play quite a role. It was, George Lucas started Lucasfilms, and a subdivision of that was Pixar, which eventually got spun off. And these, they have modelers all the time using interactive programs to develop what things will look like on the screen and try, adjust all the parameters for shading and stuff like that. It's very intensive work, and it's really, a lot of it is really done by artists. So anyway.
If I can add to that, I served on a awards committee with Ed Catmull, the guy who was the co-founder of Pixar. And he had some very interesting stories about the difference in culture between Pixar and Walt Disney. Pixar prided itself on the creativity and independence of its artists. And he claimed that that was a big factor in the success of Pixar, whereas Walt Disney was much more in the mold of a big company. And when they merged, there was some tension between the corporate culture and the artistic culture at Pixar.
And almost all films now are done by Pixar through Walt Disney. So,
yep. So artists are important.
And anyway, Paul, you still have a question? Or?
Yeah, I have another question. Okay, so we're all aware that we have computers that have CPUs, and then you plug in a graphics card, and that allows you to do certain more things, especially play computer games and so on, which are really, I guess a computer game is really the same as a simulator, except the objects are, instead of being, what you see out of the cockpit of a plane, there's sort of middle-aged warriors on horses or something. But anyway, so my question is, so what's the division of labor exactly between the CPU and the graphics card? Now, for instance, I've always assumed that the CPU has these objects defined as wireframe objects, but then it hands them off to the graphics card. to do all of the interpolated shading that's required, and also the computation of the Z computation for what's in front of what, and those computations are then burned into silicon, so they go at the fastest possible speed, whereas sort of the general scene computations are done by the CPU. Now,
Well,
is that true?
I mean, the model that I had for the array processors, there was one CPU which basically controlled the array processor. So basically it was the interface between the modeling computer to get the scene and then take those data points, because the array processor basically was 2 MACs with a bunch of cache boards. Okay, so there's multiplier, accumulator, and these things were clocked at 40 nanoseconds, and it's it takes maybe 6 cycles to get it out of an adder and 12 cycles to get it out of a multiplier. But once you fill up the queue, you get an answer every 40 nanoseconds. So it's very fast, and the buffer sizes of the cache were like 1,000. So the overhead really to fill up the buffer was very little, to fill up the queue was very little. And once you filled up, once you got the first answer, you got to answer every 40 nanoseconds. Okay. Now, if a CPU was doing that with a coprocessor, well, it would have to send, the value to be computed to coprocessor, and it would have to wait the entire 12 clock cycles to get an answer back, which is the way, desktop computers work with coprocessors. Now, if you have a graphics card, it's going to have MACs in there. And I guess in terms of the later, graphics cards, they're going to have specialized circuitry that do specific graphics functions that are not just adding and multiplying, but, clipping to thresholds, clipping to values and performing maybe some other logic that needs to be done. So basically the CPU in the computer is just a data server. It's serving up the models to the graphics processor, and the processor computes everything and brings it back. Now, these graphics processors, they have huge amounts of memory as it is. They got 4 gig, 8 gig, even more. So everything can be computed and just when it's finished, handed back to the CPU. So I think the CPU actually has very little involvement when it comes to, really high speed throughput for the graphics card, graphics output. Anyway, but, this is just based on what I know about hardware from the 80s, it has to follow something similar to that, anyway.
Mhm.
What I like to do next is I like to show, the clips that I have. So I'm going to screen share, and I hope, so I'm going to share the sound. I'm going to share optimize for video clips, and I'm going to share the screen. And I actually have to quit this one. Oops. Okay, so I like to start off, I'm going to go historically from the 1970s on up, more or less, okay? And before the first thing I'm going to show is because Griff helped me, he sent me some work that he did on a Calcom plotter. And I mean, it's out of Alice in Wonderland, and it's this text says, Fury said to a mouse that he met in the house, let us both go to law, I will prosecute you. Come, I'll take no denial. And it goes off into like a mouse's tail. Well, he did that on Calcom plotter, but he did it as a continuous line of text spiraling into a cylinder. And I just want to show you what he did back then. So you can see he says Fury said to a mouse that he met in the house, and he just spiraled this inward. But I thought it looked very nice, and it was actually had nice composition to it. You know, it's kind of artistic. So the next thing I like to show actually is in the 1990s, I was looking to buy a MacBook, I mean, an Apple iBook G4 for my wife. I went to CompUSA and they had this program as a screensaver called Marine Aquarium 2.0. And it was on every computer. And if it wasn't being used for more than 6 seconds, it would jump into this screensaver. I was so impressed by it, I bought it. And as the computer systems upgraded, I got the 3.0 because the 2.0 didn't work. But I'm going to show you this because it's incredibly lifelike. And it's got an option where I can show you the wireframe models being used. So I'm going to bring this up. Okay, does everybody see the aquarium?
Yes, we see it.
Okay, so actually there are like 15 fish to choose from. And so one is the blue tang, which is in the other one is the clownfish. And then you have the lionfish and some of the other ones, I don't even know what they are. And so you have these fish swimming around. But there's also some very slow moving objects as well. And on the left-hand side, there's like a leaf algae that's sort of, you know, undulating in the ocean current. And below the clock, there are like 3 clams are very slowly opening and closing. And if this screensaver is on long enough, it'll eventually pan over. And there's a starfish that sort of moves around very slowly. Now, after a while, the rock has a clock on it with a second hand. Okay. Now, by hitting a key, I can show you what this looks like in a wireframe model. And what's interesting is, I mean, they need to figure out the motion of each fish, how it swims, and have it, you know, and use, you know, biology and physics to make it look like real swimming motion for each fish. And each fish swims slightly different or has a different characteristic, and they manage to capture all that. So you can see how the wireframe started out to model the whole scene, and then to fill it in was just, you know, especially the fish was probably just using texture mapping. So in the end, you have this very lifelike scene, and it really looks like an aquarium. So now the next thing I like to show is, okay, so this is a program, a vector graphic program done at Bell Labs in 1963 by Edward Zajac. And I have to thank Griff for finding this for me because he sent me this. And what it is there's a model of the Earth and there's a model of this rectangular orbiting body that's going around it. And there's a clock counting off the orbits. And the purpose of this is to show that a rectangular object that's orbiting, and it may be spinning initially, but eventually the gravitation of the Earth will force it to point in one direction, in the longitudinal direction. And this is a property that the moon has, and it's also a property of satellites. So I guess this was done about the same time they were trying to send up Telstar and figuring out how to keep it aimed at the Earth. Okay, so this was originally programmed in Fortran, along with a program by Frank Sidden called Orbit. And so these computations were fed into a computer via punch card. The output was printed on microfilm using General Dynamics electronic Stromberg-Carlson microfilm recorder, and all computer processing was done on IBM 790 or 794. And then obviously out of that, they had to piece it together into a film or, so I'm going to, okay, I think I can go full screen on this and I can play it. And it has some sound to it. So if you listen to it, they'll explain it.
This is a computer-made movie. The box represents a satellite, which is now in a circular orbit going over the poles. In the upper right, a clock counts off the number of orbits. Gravity gradient torques force the satellite's long axis to point toward the Earth. Exactly this effect keeps one face of the moon always pointing toward the Earth. This is very useful for weather or communication satellites, where either an Earth-pointing camera or an Earth-pointing antenna is desired. In the rest of the movie, we shall look at the satellite only in a reference frame that is orbiting, as the satellite is doing now.
Okay, so there you have it. That's probably like the earliest CGI ever done. Okay, I have two clips from Tron. I mean, computing power was very limited. They really just deal with, most of the scene is simple lines. There is some shading, as you can see, with these light cycles. There's also real actors that they have like a coat of CGI over them. And I think one of the Bridges boys is one of the actors. So I'll just.
This is Blue Leader to Blue Bikes. Run these guys into your jet walls.
Copy, Blue Leader.
Copy, Blue Leader.
This is Gold 1 to Gold 2 and 3.
Split up. Take them one-on-one.
right now, and you guys are invited. Got it.
Ready? Ready. So long, sucker!
You must return to the grid.
Now, let me ask you, did the video play properly without any skips?
Yeah, it was pretty good.
Yeah,
Okay.
it was good.
Now the one that's even this is the other one. this was showed at SIGGRAPH when I was there in 1982, and this, people went crazy over this one. So anyway, I mean, you can see that most of the graphics is still pretty simple, with the exception of a couple of key pieces. So this thing is a solar sailor that sails on a beam of light. So anyway, I mean, the whole plot behind that is there was MCP, Master Control Program, which had turned evil or something like that, and they went into the computer to battle it. Anyway, this clip here is a short clip from the works, which never got finished, and you get to see. Now, for some reason, the resolution is, the clarity is not very good on it. But graphically, it's far more advanced, but it's so advanced that they weren't able to compute the entire film.
I gotta take off a couple minutes. I'll take over the rest of the duties. I'll take care of the video. Okay, see you later.
Now, the interesting thing about this is after the effort collapsed, all the people either went to Utah or they went to Pixar after this. So now this one is like like more than a decade later. And the interesting thing about this is the graphics has greatly improved, and it's a much better storyline, and this is like the first Toy Story.
Sergeant?
Yes, sir.
Establish a recon post downstairs.
Code Red, repeat. We are at Code Red. Recon Plan Charlie, execute. Move, 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 move. It's a big one.
Walt Disney Pictures presents
Star Command, come in. Do you read me?
The Story of Two Toys.
There seems to be no sign of intelligent life.
Now, let me just stop it at this point. Now, even though I believe this whole film uses polygon representation, they still have this clear plastic bubble that's, that they have to deal in a refractive manner. Now, I'm not exactly sure how they did this, because I'm pretty sure they didn't use ray tracing here, but
sign of intelligent life anywhere.
Hello?
Headed for a showdown.
My name is Woody. This is my spot.
I am Buzz Lightyear. I come in peace.
You are a child's plaything!
You are a sad, strange little man.
And playing by their own rules.
Draw! Got me again!
I don't like confrontations.
Buzz-looking alien!
Where?
You're mocking me, aren't you?
Oh, impressive wingspan. Very good.
Oh, what? What? You can't fly.
Yes, I can.
Can't.
Can.
Can't!
The adventure takes off when toys come to life.
To infinity and beyond.
Toy Story.
Look out!
Can.
Okay. So this, Toy Story also had Randy Newman that created the main theme for it. Oops. Let me just get this one here.
You're my favorite deputy. Buzz-looking alien! Where? I'm Picasso.
Now, it also turns out that that Don Rickles voiced Mr. Potato Head. So I'm going to back it up just a little bit because he did basically a Don Rickles scene here.
Picasso.
I don't get it.
You uncultured swine. What are you looking at, you hockey puck? It's not a laser. It's a little light bulb that blinks.
What's with him?
Laser and
Look, I'm Woody. Howdy, howdy, howdy.
Give me that.
Now, one other thing I want to mention is while they're real people in this, they're kind of stylized and they give only a few seconds for each one. They really concentrate more on the toys.
Pizza Planet? Pizza Planet? Oh, cool! Mom, do you know where Buzz is?
Ma'am, well, I just want to say you're a bright young woman with a beautiful yarn full of hair.
For infinity and beyond.
Hey, cowboy.
Come with me.
What?
Andy will play with all of us. I know it. Oh, no.
And as the years go by.
I'll just stop it here. Now, Toy Story 3 actually had something that was very philosophical. And I'm just going to play this small section of it then.
This is an intergalactic emergency. I need to commandeer your vessel to Sector 12. Who's in charge here?
Claw's our master. Claw chooses who will go and who will stay.
This is ludicrous.
Hey, Bozo!
So anyway, so I'm going to fast forward to about another 10 years, another decade.
"700 years into the future, mankind will leave our planet, leaving Earth's cleanup in the hands of one incredible machine.
Now, the one thing about this is this robot looks very similar to the one used in Short Circuit, which is an all-human actor thing based around a robot. The other thing is, graphically, they, instead of making everything nice and clean looking, they concentrated on things being dented and dirty and stuff like that. So that was, that takes additional modeling effort. So I just want to point that out.
His name is Wally. After all these years, he's developed one little glitch. A personality. He's extremely curious. And just a little bit lonely. But all that is about to change.
Arrest that robot!
10 seconds to self-destruct. You are now free to move around the cabin.
Just a tram? You look gorgeous.
Anyway, they featured Etta James' song At Last in that picture. And now this one, so now we're up to 2016. And the thing I like to point out here is that you have windblown hair, you have more realistic looking people, animals, vegetation, clouds, and water. So, the amount of effort spent in modeling all those things had panned out. So I'm going to. And notice they got the water really quite nice, So this is pretty advanced. Okay, so now I'm going to step back a little bit. So back in the 70s, I had a Swedish lamp called the Ledu lamp. So this one appears to be of a similar design. The Luxo L1 is the original architect and designer's lamp. It was designed in '37 by the founder, Jack Jacobson. An animated version is now part of the Pixar logo. This was done at Lucasfilm's Pixar division by executive John Lasseter team. It was initially shown at SIGGRAPH 1996 SIGGRAPH conference and received a standing ovation. It was the first CGI film nominated for Academy Award. And note that the same ball used here was used in Toy Story. So Okay, so this one is one done 33 years later. Better realism, more sophisticated. The software used was Blender 2.8, Adobe Premiere Pro 2020. So so he's asking, can I go bowling? Okay, this goes on for quite a while here, so I'm going to go to the next one. Actually, these are the last two. I'm I'm not entirely sure how this was done, but it has the quality of ray tracing. And this is the Geico gecko. The gecko's name is Martin, named after the ad agency that created him, and is voiced by Jake Wood from the EastEnders. And notice the reflective quality of the eye, a sign of ray tracing, also the out of focus effects. So I'm going to play this one here.
Yeah, I mean, the thing is, people like Geico because it's just easy. Bundling, for example. You've got car insurance here and home insurance here. Why not? Zoop, put them together. Save even more. Some things are better together, aren't they? Like tea and crumpets. You wouldn't bundle just anything. Like, say, a porcupine in a balloon factory. Now, that'd be a mess. I mean, for starters, porcupines are famously no good in a team setting.
Geico. Save even more when you bundle home and car insurance.
Do you want more funny videos? Just click that subscribe button and share too. No, a little more left. Now down. Down. No, it's too far.
Just show one more. This one has raspberry jam, which looks incredibly lifelike.
It's just about time, you know. It means experience. I mean, put it this way. If I told you I'd been jarring raspberry preserves for 85 years, what would you think? Well, at first, you'd be like, that has got to be some scrumptious jam. And then you'd think, he looks fantastic. I must know his skincare routine.
Geico, saving people money for 85 years.
Beg your pardon. Do you want more funny videos? Just click that subscribe button and share too. No, a little more left. Now down. Down. No, too far. Well.
Okay. Okay, that's pretty much all I have here. I'll send out the links in case the sound didn't come through or the video didn't come through properly or the resolution didn't come through properly, because some of them, when I go full screen, they tend to blur out. So does anybody else have any further questions or?
Guess not. So Joel had to leave early, so he asked me to finish up here. So thank you, Walt. That was fabulous. Wow, very informative and very entertaining. So thanks. Anything else? Anybody? Parting comments?
So hopefully you'll all be connoisseurs of fine computer animation graphics. You'll know what to look for. You'll get an appreciation for what went into it.
Maybe we should roll up our sleeves and do some animations. But
I'll say, Walt, that was
coding team.
absolutely amazing, and I'm amazed at the effort that you had to put into that, and of course your own personal history there. I do get the feeling, looking at that whole sequence from early to now, that it's gone from what used to be one or two people working on something to a team or maybe even a corporation working on something to get it done. Any sense for that?
Yeah, yeah. I mean, I mentioned that the works which was done in the 80s, they had a team of 60 people, and I'm sure it's in the hundreds now, because anytime I see anything on Pixar, they got an incredible number of people working on it. I mean, all skill levels are needed. Some people have to, I mean, some of the processing power was custom designed just to do graphics. And, obviously the people have to maintain that, people have to do the animation. Usually when they do the animation, they do it in smaller pieces and simple, maybe just wireframe models just to make sure they work out, because the time doesn't take so long. And then, when they get something worked out, then they'll put in the color, the texture mapping, whatever else they have to do. And then, and maybe they check out some of the fancier algorithms just for a piece of it. But then in the end, they have to let, crank out the whole movie in full glory. So, and I'm sure it takes hundreds, if not thousands of people, working at Pixar. I'm not even sure how many people they have, but
I have no doubt that they have developed some very high level tools for managing a lot of, they're not doing all that low level work anymore. They have tools that are designed for making these animations, and they have collections of piece parts that they can pull off the shelf and dust off and put together in different ways. I'll bet they've got all kinds of shortcuts.
Well, a lot of it is just the interactive tools that they develop to build the models and check them out and all that kind of stuff. That's enormous software work by itself.
Like instead of writing down equations and writing code, they probably have consoles, with multiple controls, and they can just sort of, like in a video game, they can probably, essentially program certain things just by moving controls. That'd save you a lot of time.
Yeah, I'm sure there's probably just a few key people pushing the algorithms to better and better detail. And then when they release them to the animators, they just, you know, they have all the controls that they need to make it do what they want. But
I might mention that we heard from Sri Nair in January. He talked about computer vision at Columbia University. Some of his colleagues, one of them in particular, Eitan Grinsman, has been working in this area of rendering objects. You talked about rendering hair. He's had a couple of PhD students who've created algorithms to render hair. And there was a movie called Rapunzel that used his techniques to represent the hair of Rapunzel, you know, the long tresses coming down from the high castle, high tower. So the sophistication of the algorithms that are being used, and you mentioned the rippling effects on the water. These are the subjects of PhD theses today, and the mathematics that's used is just very, very sophisticated. So it was great seeing an introduction to how the mathematics has progressed. It might be nice to see how modern mathematics in this area works, but it's so sophisticated, I can't understand it.
That makes it tough for mere mortals like us.
I'm sure it's beyond high school mathematics by now. You know?
Anyway, it was a great talk, Walt, and entertaining as well as enlightening, and you'll be a tough act to follow.
Yeah, I'm gonna send out a link of the, you know, a copy of the slides, and the slides will have links to all the videos that I showed. So if anybody wants to replay them and see them, you know, I don't know how the sound came out or the video came out, but you know, if you run it on your own PC, they'll come out pretty much perfect. So anyway, all right, thank you for all attending. So next time we'll have another interesting speaker. I'll announce it next month.